Can cheaper radios handle short distance? Visual cells may serve in more non-photonic applications. Optical technology is well established for long-haul communications, but the distances it serves are shrink, especially in the data center. Vertical cavity surface the emitting lasers. Visual cells already drive shorter fiber rings, but efforts are underway to further scale them down to provide more connections through waveguides than fiber can provide. Though we have seen the transition from long-haul to metro to local area networks and then into the data center, said Sreshi Jayalaman, Senior Director for Package Developed for Amcor Technology. Fiber has moved from the edge of the card to onboard and more recently onto the package. This research is still underway to move optics closer to servers in the data center. Today, the technology typically is employed for rack-to-rack communication, while most intra-rack wires are copper. Replace the copper with the fiber remains a development opportunity. The integrating lasers with silicon. Of particular interest is where the fibers will attach to processors. Standard pluggable formats may give way to linear pluggable optics (LPO) and the co-packaged optics (CPO), but those are still in development. Three lasers attributes dominate the concept over how to integrate the optical communication reliability, temperature sensitivity, and energy consumption. Reliability has been a top concern, and although it's improved, developers are still concerned about soldering a laser onto a board in the case it goes bad and it must be replaced. This is the central motivators for pluggable formats. The good news is that the lasers are getting pretty robust and pretty reliable, not comparable to what they were in the past, said Mitch Hines, Senior Product Manager at Synopsys. But designers remain wary. Lasers are notoriously sensitive to changes in temperature, and that can be challenging when the precise wavelengths are necessary. Note that the electronics we typically define speed in terms of frequency or hertz, whereas in optics we tend to speak of the wavelength, typically in nanometer. Finally, energy is important. The obvious energy consumer is the laser when operating, but the related aspect of the power is the laser threshold. That's the minimum current necessary to stimulate the raging. The current is entered for laser power, and the higher the threshold, the more current will be constantly running. Efforts therefore focusing on establishing lasers with a high reliability, low temperature sensitivity, and a low threshold. Incumbent lasers. Today's optics often rely on so-called distributed feedback lasers, DFBs. These are well-behaved structures that are threshold in mid to low milliamp range, which is lower than some other types of lasers. This technology represents a scaling down of the long-haul optics for shorter distances. The lasers typically operate in one of the two bands, C or O. The former is centered at a 1550 nanometer wavelength, while the latter is at a 1310 nanometer. The O band has a higher signal attenuation than the C band, but it has lower dispersion, which refers to the spreading out of symbols that can smell into each other. The C-band range has a low attenuation but higher dispersion. It lends itself to the Iberium-doped fiber amplifiers, ERFAs, that help signals cross under the ocean. In the data center and within a rack, loss is important, but the distance down requires RFFAs so that the C-band adds no value, though it's certainly unusable. Whichever the band is employed, the FBS provides a clean single-mode radio source that can serve interconnects. BFP lasers are better. That is, where the narrower line width and the larger bandwidth is a higher optics output power that they can operate in O and C band. That they are also more expensive, said Jigesh Patel, principal engineer the photonic systems and circuits at Synopsys. So they are typically used to follow long reach over single-mode fibers. The FP lasers are also better suited for coherent fiber optic communication, with some said they eventually move inside the data center. And wavelength division multiplexed fiber optic systems, partly because of the single-mode operation with a narrow line width and partly also because of it supporting much larger operational wavelength band. Much of optics research underway drives the development of silicon photonics, where the photons do more than travel from here to there. They perform computing along the way, just as electronics do in electronics. As such, no optical development that don't fall further the technology might be bypassed. And yet, effective interconnect should be possible without meeting the needs of the photonics. Temperature control drives system configuration. Of the challenges developers face with lasers, the big one is managing temperature. You have to do something either to control the temperature of the device in the rack, which is tough because you're controlling something of the order of the 1 degree, so on. Also, the said Dick Otto, CEO of Promax, we've seen cases in which people are trying to control the temperature of the optic devices to as fine as 1/10 of the degree centigrade. Aesthetic control. Those margin is sufficient for signaling formats such as PAM4. Variation in temperature causes a dimensional variation in the laser, so which changes the frequency enough to get things out of band and reduce the signal to noise ratio, Otto said. So when you start utilizing things like PAM4 and PAM16 as modulation schemes to maximize the amount of data, those schemes start to failure. Although CPO remains a goal, whether to include the laser remains open as questions. Most experts lean toward keeping the lasers out of the package that houses other electronics and optics for easier temperature control. Laser proximity to a higher temperature chip, such as a processor, is a particular concern, especially as activity rises in force, leading to temperature changes. The lasers have most stayed out of sight of the package due to the area and power concern, said Jayaraman. Laser performance and reliability lifetime also improved if it is decoupled from the package, even though the optic coupling loss of the edge bandwidth density is an issue that are needed to be addressed with remote laser sources. Steve Klinger, vice president of the product at Lightmare, agreed lasers are relatively temperature sensitive, so having them physically separated from the rest of the silicon and being able to locate it where else the system is advantageous. It may even make sense to bring lasers together in a single, carefully controlled model. Fiber can still bring the light to the co-packaged circuit, avoiding the current situation where optics are converted to electrical cells to the drive chips, an energy-hungry approach. The lasers come in on some number of the fibers that are edges of the package, and they are separated from the package for two reasons, said Klinger. One is the most serviceability of the major laser. The second is just the sheer amount of laser power that is needed to power a very large scale. So the number of the laser lends itself toward integrating the laser in a separate physical module, and the module plugs into the out of the system. Work continues, however, on other ways to house lasers, which largely rely on a 3 to 4 semiconductors. The typical package scheme is to create a cavity in silicon in which to insert the laser, assuming it's an edge-emitting model like most lasers. By embedding it in a die, the lighting coming from the edge can enter a waveguide. So the figure 1 is the edge versus surface emitting lasers. The top image show an edge emitting model embedded in silicon. The bottom depicts a surface emitting laser on the scale's backside. 8 of the silicon with a mirror integrating the couple to send the light into waveguide. Source: Brody on Moia Semiconductor Engineering. The further work continues to grow 3 to 4 materials epitaxially a top silicon. If such as a laser were edge emitting, effort would be next to route the emitting light down into the silicon. There is a lot of active research around integrating 3 to 4 materials onto silicon substrate, such as monolithic integration, heterogeneous integration, and transforming permitting, said Yaraman. However, none of these appear to ready for high volume. Heinz agreed. People are working on all sorts of solutions, whether you grow 3 to 4 silicon or whether you cut a hole in the silicon and drop a laser die into it. Meanwhile, the work continues on a quantum dot QD lasers, which have a less temperature sensitivity but lower output power. QD lasers are largely found in displays, where their color purity and tunability make them particularly attractive. The visual cells may have a new application. Visual cells are easier to build, that is, cheaper lasers that are found in a variety of the systems, such as optical mice, as well as shorter data center connections. If the infrared type short-reach connectivity uses multi-node optical fibers, visual cells are the optical choice, said Pytel. They are easy to manufacture for wavelength for their multi-node fibers use and loss less, and 850 nanometer is the choice at the visual cells manufacturing technology is the most mature. The visual cells have some issues when considered in the context of the silicon photonic. However, those issues may not matter for the interconnect role, and the further development have improved some of their other characteristics. To start with, their wavelength is the O band and C band. Many are centered at 850 nanometer, with some new ones at 980 nanometer. Efforts are underway to create visual cells with longer wavelengths, but nothing is in the commercial production yet. Visual cells that operate in the O band are desirous but difficult to manufacture with a good yield, explained Patel. Remarkable progress has been made in the last 3 years, not only to make O-band visual cells happen, but also with much wider bandwidth than in the past. And newer modulation formats such as PAM4 and DP-PAM4 can achieve much better spectral efficiency than the bandwidth of the laser device itself. Both high bandwidth O-band visual cells and PAM4 has reinvigorated interest in using visual cells in the O-band and single-mode fiber, something that used to require the BFB lasers before. Some VISA cells apparently also exist 1550 nanometer, but they are not mature yet. Mature yet. So even as long as the photodiodes at the end of the waveguide that convert the optical signals back to the electrical can responded efficiently, and as long as there is no interoperability question with other optical components, the specific wavelength may matter less than the interconnect. Their output is relatively wideband. This is a problem for photonics, which employs components such as a resonator that need precise wavelengths. Again, for fewer interconnects, this may not matter. Fischer's power is too low for photonics, although it can be adequate for interconnect, but it's slow to modulate if using the directive modulation as compared to the speed necessary for photonics. Direct modulation involved running the electrical communication signal through the laser itself to create modulated optic signals. It contrasts with generating a pure laser beam and then modulating the beam afterward. If you want to direct modulate them, they are slow, and there's a big reason why the Fischer cells have fallen out of favor. And Tapagoshi, founder and CEO of Volantis Semiconductor, they also exhibit multiple modes and polarizations. These are characteristics that might either help with the long-haul communication, where many signals are aggregated and multiplexed into few long-distance lines, but they are not useful for extreme short point-to-point connections. VISA cells in the data center typically drive fibers and indicated the lane. VISA cells emit their light perpendicular to the surface and concentrate edge emitting lasers such as BFBs, and this can make integration easier with vertical light from the backside emitting lasers reflected into waveguides using mirrors. A big win here is power. Whereas the DFBs have a milliamp threshold, VISA cells have thresholds in the hundred of microamps. 10 VISA cells can tamed. These characteristics are mixed bag, some good, some unhelpful. Volantis, an optic startup, said it has engineers and improved the 980 nanometer VISA cells that's a single mode and a single polarizations. The company is combining the wafer that acts as an optic interposer with the grating couplers to emitting the laser light into wavelines and photodiodes to convert back to the electrical domain. Figure 2. VISA cells used for an optic interposer. Volantis' first generation implementation had a 3D area of VISA cells that a couple of one's wavelengths using a greater coupler GC in their second generation. They plan to transfer printed VISA cells that can sit under the chip data interconnect. PD photodiodes, SIN, the silicon nitride source Volantis. These devices can be small, very small, said Ghosh. You are not doing a standard bonding here, so you can use your backside emitting devices. Among the various issues, the company says it has addressed are back reflection, which have unplagued some VISA cells, eliminating the need for attached fibers issued with mode and polarization, thermal drift, infant mortality, reliability and yield through the redundancy, simpler assembly process, and power. The laser bandwidth is 80 GHz, which is lower than 30 GHz, and so bandwidth the VISA cells are capable of but more energy efficient. The temperature tolerance is greatly improved. VISA cells in our system has about 1 nanometer shift across its temperature operating range. Said Gosh, there's no modulator that care about a specific frequency bandwidth wavelength that come in, as we are driving a 10 to 2 nanometer broadband channel, the waveguide, so that 1 to 2 nanometer wavelength shift does affect us. Volantis is starting a 3D area of the fish cells coupled into silicon for the first generation. The second generation should be a transfer printed based on the laser built on a separate wafer. After building those lasers, you'll do an etch process to create a very thin ever solid gush. And in the transfer printing process, you have an array of little pillars and their temperature onto the laser, breaking the tiny lever. And then I lift the laser of the transfer to the target wafer. Volantis claims efficiency of 139 FJ per bit, which is a big benefit of the data center. This contrasts with the BFBs and which communicate with the low and the picojoules per bit range. If you make a single mode fish cell with smaller apertures, you can get the high energy efficiency and extremely high band temperature tolerance solid gauge. There are some tricks you need to do to get this, but you get almost all the advantage of quantum dots with fish cells. The form factor is unusual, with the full wafer that are similar to the Cerebus with a custom route to the full application. So the typical acceleration would be vertical on edge is 32 U box. The speed limitation is encountered by high-level polarization, 5,000 to 10,000 signals at 25 gigabps to make up the differences. This is where the waveguards are essential because a nest of the fiber at the level of the unworkable. If this proved to be effective, it could boost fish cells adoption. If a wafer scale approach is essential to achieve power efficiency goals, however, in the application space is likely to be limited. But if the developer can leverage improved fish cells in a smaller installation, then they could add to the options available for heterogeneous integration. Even if the particular fish cells does play out of the volunteer house, it seems like that new cells with longer wavelengths are likely to start integrating that data center in the future. We just don't know where. Editor's notes. The original particle was okay. Today I like this article. The can cheaper lasers handle short distances. Thank you for your time. See you next time.